Hello everyone. Welcome to the what is probably the last lecture session for Unit 5. This session I will introduce the concept of statistical STA. This is where the STA methodology is moving towards SSTA, given the lot of complexities in technologies that are lower than 45 nanometers. Although we are not at a stage where we are doing 100% STA, but we are using some of the tools or some of the methodologies that are somewhat statistical in nature. So till the so I would say ST methodologies are divided into kind of two types. One is till OCD and other is beyond OCD. So in the last session we discovered what OCD was, what concept variation was, and we saw the methodology where we select one operating condition for one run, and within that operating condition we use timing delays to model the onset variation. Now this is not we will see in this session that why this is a comparatively shorter presentation, but we will see why this is not good enough, or why this is not sufficient, or why this is proving out to be a lot more complex for technologies beyond 45, and we will see what sort of technology is replacing it. Let's first look at a Gaussian and a normal distribution. So Gaussian distribution is a continuous probability distribution that is used to describe real valued random variables. This is very essential now. This is the concept of random variable is very essential to the whole process of statistical STA. Now consider let's discuss a non-semiconductor scenario. Now let's say you one of you goes ahead and tries to map the height of an you can choose, let's say you want to map the height of all the people in one particular city, of let's say all males in one particular city. Now there will be the data will be in number of lakhs or crores even for a big metro, and you will find that the data is concentrated around an average value. So it will be a bell-shaped curve, a Gaussian curve, which will be the average of it will be concentrated around the average of that. So this is a random variable. The height obviously is a function of genetics and all that, but when you measure height of a big sample size, the variable itself becomes random, but it is focused around one particular average value. Same thing happens in fabrication. In fabrication, let's say for 45 nanometer process, there are millions of transistors on a particular chip. Not all transistors will have exactly 55 nanometer length, channel length. Some will have less, some will have more, but again they tend to cluster around. This is the idea. They tend to cluster around a single mean value. The probability distribution formula is this: 1 by underscore root 2 pi sigma square. The sigma is the standard deviation, and mu is the mean. So mu is the mean, and sigma square is the variance, the measure of width of the distribution. The square root of sigma square is called standard deviation. Right? So you don't need to remember this formula. You just need to understand that any such variable in a fabrication process will have a random distribution. In fact, it might not have a completely random distribution, but it is being modeled as such. We are modeling, it's an approximation. Again, see, the idea here is that continuous, what we call as CPD, is the used as a first approximation. The variable under scrutiny might also have a different kind of distribution, but most of the variables that affect the performance of the chip, like channel length and thickness of the oxide and so on, they can be approximated as a Gaussian distribution. There are other probability distributions also, but we will be focused on the normal distribution. The graph is something like this. Now on the upper hand, on the upper half of the slide, you can see three normal distributions with means mu is equal to 0. One, the blue curve is this one is mu is equal to the mean is 0. It's centered around 0. and the standard deviation is 0. So variance is 0.2. Standard deviation will be square root of that. The red one is again mean is same, but variance is a bit more. The third one, the yellow one, the mean is again 0, but the variance is still more. So you see that, observe that the greater the variance or the greater the standard deviation, the wider is the curve. What it means is that standard deviation is a measure of the total width, the width of the Gaussian curve. The green one here is the mean is -2 and the variance is 0.5. So as an engineer working in fabrication, the idea is to make sure that the standard deviation is under control, because the greater the standard deviation, the greater is the variance. That's what it literally means, right? So let's say examine the yellow curve. Let's say this curve represents the channel length of NMOS devices. Now this is not what you want. You don't want, and let's say the average is 45 nanometer instead of 0. Now this kind of wider distribution you don't want, because this is telling me, this kind of curve is telling me that yes, there are so this is number of, this is here, this is the probability distribution, right? Or you can even say number of devices. So if number of devices, okay, yes, there are maximum number of devices at 65 nanometer, but a lot more devices are showing channel lengths which are greater than 65 nanometer and less than 65 nanometer, and the curve is pretty wide, right? We don't want that. We want a curve of this kind, which is sharper, less wide, which has less variance, less standard deviation. This is what manufacturing tries to control, right? Now, one more interesting statistic is that if you take area around the mean value within 1 sigma, within 1 standard deviation, 68% of the area under the curve is within 1 standard deviation, 95% of the area is within 2 standard deviation, and 99.7 area is within 3 standard deviation. This is the fact. The third one, 99.7% area is within 3 standard deviations. This is the idea behind the corner based analysis or SSPA both. That is, we try to find a corner in corner based STA which covers up to, so let's say you plotted the device delay. Now the -3 sigma will be faster devices, plus 3 sigma side will be slower devices. So if you want to cover almost, if you want to have the yield which is more than 99%, you will try and sign off at ±3 sigma. This is the important figure here, ±3 sigma. This is important here. So we will look. Let's go to the next slide to make this thing more clear. Okay, let's. Okay. So the idea is whatever corner is chosen for corner based STA. There's one more slide which. Yeah. So this is the slide I'm talking about. So corner based STA, we should try to choose a corner which covers up to 3 sigma. Slow corner on the +3 sigma side, fast corner on the -3 sigma side. This is just an example I'm giving, because there are hundreds of parameters in fabrication, right? This is one parameters where we have plotted channel length and number of samples. Again, we get a Gaussian curve. So we will get something like this. We will get a curve something like this around the mean value. And now we are choosing a corner somewhere around here and here. And this is the way we target that my yield should be more than 99%, almost, or rather almost 100%. So the yield is never 100%. There are some problems, some outliers, but this is the idea, right? So, okay. Now let's talk about process variations. How many types are there, and what do we model, how and how? So process variations are of two types: systematic and non-systematic. Again, systematic, so systematic are the ones which are, I would say, they are problems in the fabrication. They are something which are not acceptable. Something like saying that the thickness of the oxide is lower than some critical limit, and or the channel length is beyond a particular permissible value. So systematic process variations are not handled in SPA or SSPA. They are handled in the fabrication process. Fabrication process should be corrected to get rid of these, right? Now we come to non-systematic. Non-systematic are the ones which SSTA or STA, traditional SPA tends to model, right? We try to model these non-systematic variations. Now, non-systematic variations again can be from die to die or within die. Die to die means they are they vary from die to die. They affect one die more and one another die less. It can happen in a particular wafer. In a particular wafer, the dies that are lying at the center of the wafer might behave somewhat differently than the dies that are lying around the corner, around the periphery. So it may happen. Again, there are systematic variations, non-systematic variations within die. That means parameters affecting the performance of different devices differently, right? Now again, the within die are of two types, which are spatially correlated and other independent. For example, let's take two parameters. Let's say take the channel length of the CMOS and let's take the thickness of the oxide. Now these two parameters, if they show no correlation to each other, that means the distribution of one is entirely independent of distribution of other, then they are independent. But if we figure out that in a particular area, the devices that the PMOS devices that have high channel length, for example, they also have more thickness oxide, then they might be spatially correlated. This is very important for SSTA. SSTA needs to know whether the parameters in question are they independent or are they spatially correlated. Now let's look at die to die variation. This category, non-systematic, die to die. Systematic, as I told you, systematic is more for they require correction in the fabrication process, and some of the within die variation you cannot fix your fabrication process how the things are. So let's look at the die to die first. Die to die variations are called global variations. Also, the more famous term is global variation, die to die or inter die. They are variations in process parameters which affect all devices on a die similarly. That means within a die, these variations are not within the die. They are from die to die. That means that within a particular die, they affect everybody similarly. So let's say there is some issue with the fabrication wherein the dies on the corner have slower NMOS devices. It can happen, or slower PMOS devices. That means that all the PMOS on the corner chips are slower. This is a die to die. This is an example of die to die variation because all the PMOS are generally slower than compared to the die on the center of the chip, right? So here is one example where we plot number of samples and we plot a parameter called GP1. We get a Gaussian curve. Now in practice, for example, the example is that G1 parameter may correspond to the device threshold, the VT value for a standard PMOS, right? Now we already know that GP1 is a global. So PMOS devices in all cell instances of the die will correspond to the same value of GP1. That means, let's say for a particular die, if you plot GP1, it will look like this, right? Now let's say for a different die, you plot GP1 again, it might look like this but slightly shifted. The distribution is same, almost same, but the mean may be slightly shifted. So this is die to die variation. Now non-statistical STA is also called deterministic STA. So in this case, the slow process model will belong to the plus 3 sigma format. Fast process model will belong to the minus 3 sigma format. Die to die variation is handled in deterministic STA by assigning a particular corner, a worst case corner or a best case corner. What will that worst case corner will be? Now let's look at this curve a bit differently. Let's see that this curve, assume that this curve is GP1, but its now number of samples is the number of dies. So the parameter of GP1 is nothing but the average value of GP1 across number of dies. Let's say I plotted this GP1 across, let's say, 1000 dies. Now at a particular die I took one average value of the GT of PMOS on every die and I plotted this. Again I will get this type of curve because there is a global variation. Now I choose a plus 3 sigma corner and a minus 3 sigma corner and do deterministic STA. This will ensure that all these samples are captured in my STA, right? So this is what deterministic STA does. So corner represents, so that's why we call in corner based STA, we call the operating condition to be a global corner, right? Because it corresponds to global variation, right? That's what we discussed, right? That's what we discussed in the different sections of STA, wherever we talked about operating condition. Is that operating condition represents the worst case scenario across all dies. It's a global corner. The process SS corresponds to the worst case corner, worst case condition, and that is the plus 3 sigma condition. Similarly, fast case represents the fastest condition, fastest where a particular parameter will yield into a fastest device across all dies. So this is again a global corner. Now second type of variation what we saw was within die variation or local variation. This is also called intra die, within die, or local. Local is a more famous term for it. It refers to the process parameters which can differently affect devices on a given die. Now this is the effect where all the devices on a particular die are not uniform. So it is intended to capture the random process variation within the die. The process, even if the fabrication process is correct, is absolutely, it cannot be perfect. No process can be such that it manufactures millions of transistors on a particular die which has the same parameter, right? So this is the graph where global variation obviously is a much wider curve, and within this let's say we plot the delay and number of samples. So global variation would be a much wider curve, obviously because it is across dies. It takes into account lot of dies. The local variations can be, let's say for this curve can be for one particular die, this curve can be for another particular die, this curve can be for some other die. So typically what will happen, this die will be a typical die, this die will be a slow corner, and this will be a fast corner because we are plotting delay, inverter delay with respect to the number of samples. So a typical would lie somewhere in middle, slow will lie somewhere around plus 3 sigma, and fast will lie somewhere around minus 3 sigma. So within die variations we saw that there are two types, purely random. The one effect is independent of other, second is spatially correlated. Processes tend to affect the imperfections in the processes tend to affect closely spaced devices in a similar manner. If such thing happens, then it's a spatially correlated variation. This makes them more likely to have similar characteristics than those placed far apart, right? So please remember these two things. Random is completely random of each other. Correlated ones, they are dependent on the proximity. Similar devices in a that are closely spaced will have similar variations, right? Random are not related to each other. So some of the effects can be purely random, some of the variations can be linked to one another. So this is the essence of the local variations. There are two types, random and spatially correlated. Now we have already discussed what corner based STA does. It tries to address the global variations, right? And what about local variations? Local variations are taken care by the OCD. We'll see. So now the problem with corner based STA as we go deeper and as we go smaller and smaller is that the variations are now, there are so many types of variations which we cannot ignore. There are metal variations which can range from -10% to 25%. There are environmental variations voltage island in low power devices, IR drop, temperature, device fatigue, NBTI. This is negative bias. I think this NBTI stands for, I think, negative bias threshold something. There are hot electron effects. These effects are not, they were negligible for 90 nanometer onwards, but as we go smaller and smaller, these effects are now very much pronounced. Again, VT and TOX tracking, hardware modeling uncertainty, mathematical errors, NLP mistrack, fast rise, slow fall, slow rise, PLL. So all these variations that were earlier very small are now becoming bigger and bigger. So if you want to, in a corner based STA, if you want to make sure that you take care of everything, you count all the corners, then it says some 2 to the power 20 timing runs. I guess maybe yeah, because how many 1, 2, 3, 4, 5, 6, okay. I'm not sure where 2 to the power 20 comes from, but the guard band is minus 65 to 80%, which is a huge guard band. You cannot verify this with corner based STA perfectly. So if you make sure, if you, let's say, you will somehow one way or the other, you will miss out one particular corner. That's why I'm saying earlier I used to do STA on 2 corners, corner based STA. Now I'm doing STA on 6 to 8 corners. The corners are increasing because of this variation, right? Because of so many variations. Earlier, the variations like device fatigue were not even of any consideration, right? So this is where the problem arises. So let's look at the corner based analysis and see how it tries to model the local variations. We saw OCV, that OCV is a way to model the local variations, and how does it do? So now let's say I'm working in a session where OCV is set and timing the rate is also set, right? So let's consider this path of 4-stage path. So each delay here, each AND gate here has a typical delay which comes from the library. It has a min delay, which is because of the set timing delay command we have applied for OCV. Again, it has a max delay because of the timing delay command. So each of the gate has min, tip, and max delay. Cumulative, this ranges to, we'll add all the min delays, we'll add all the typical delays, we'll add all the max delays. So this is min delay reported, this is max delay reported. What the basic ST analysis is conservative in the sense that it will overestimate the delay of long paths. Why? Because it is assuming that all 4 AND gates are at their slowest. For example, when it computes the max path, it is assuming that all 4 AND gates are slowest. So this slowest delay is 0.052. For hold path, it will assume that all AND gates are fastest, right? Therefore, but what is the reality? Reality is this may be fast, but this may be slower, or this may be slowest, and this may be again fast. This is the reality because of the local variations. Not all the devices will be slower. So this is why we say that it will overestimate the delay of long path. So let's say delay, the actual delay will lie somewhere in between. It will lie somewhere here maybe, but it will overestimate the delay on the max side. It will underestimate the delay on the min side. This makes the analysis safe, guaranteeing that design will function at least as fast as predicted on the setup side and will not suffer from hold time violation. So this is the guard band, which is very wide because it overestimates the delay of the long path, max path, and underestimates the delay of the min paths. This is the way it makes sure that the analysis is safe from the performance point of view and there are no hold time violations, right? This is why we say that corner based STA in most of the cases is pessimistic, right? Okay. So traditional STA is deterministic, means that it tries to define a corner. It tries to, that means the slack value is either positive or negative and there is only one value. That's why we call it deterministic. Traditional STA will tell you whether the path is met or violated. That's it. It computes the circuit delay for a specific process condition because it's a corner based STA, all parameters that impact the delay of the circuit, gate length, oxide thickness, etc., are assumed to be fixed and uniformly applied to all the devices. Operating voltage and temperature are uniformly applied because we choose a corner for that. The device gate length, anyway, oxide thickness, these are not direct. These do not influence the SK directly. These are part of the PVT. So this is operating voltage is V, temperature is T, oxide length and oxide device gate length and oxide thickness are part of the P. It takes care of the global variations by creating multiple corner files and no statistical way of modeling within the variations. There is a way, OCV is a way, but OCV is not statistical in nature. OCV is deterministic in nature. OCV assigns fixed guard bands and which tell us that whether the timing is met or violated. It is not a statistical way of modeling. What it means? It means that the effects, the physical effects, they are statistical in nature, but the modeling is not statistical. We are using a fixed guard band based technique to model the statistical physical delay. What is ideal? Ideal is what if people could model the variation which is physically statistical also in a tool. In a tool, can we also model them as statistical? Let's see. This is what SSTA tries to do. It models non-systematic variations as random variables. Remember, non-systematic. Let's go back and see the categories again. So it only models non-systematic, right? Not the systematic. Systematic, as I told you, has to be corrected in the fabrication process itself. These variables can be uncorrelated, partially correlated, or perfectly correlated with. And deterministic STA and SSTA differ in the way they treat correlations. This is the new thing about SSTA. SSTA, the deterministic STA will assume that all the variables are correlated. Why? Because it assumes that, for example, for max delay, it assumes that all the gates have maximum delay. So it is assuming that all the parameters for max delay calculation, all the parameters that result into a device being slower are applied at the same time. So they are all perfectly correlated. For example, what happens? Let channel length is bigger, VT is higher, and all that. Both these will cause a device to get slower, right? So it assumes that all these devices have more VT, all these devices have more channel length. So it assumes the worst for all the devices for max delay calculation. For best min delay calculation, it assumes the best conditions for all the devices. So it assumes that all the variations that are causing all the parameters that are causing the variation are perfectly correlated. This is where SSTA is different. SSTA tries to model the variables as it can also model the variables at perfectly random, that is uncorrelated, partially correlated, or perfectly correlated. And this is what happens in the real world. This is what happens. Not all variables will be perfectly correlated. This is what SSTA models, right? So let's see correlation. Let me first clarify a couple of things about correlation. Correlation represents the statistical relationship of two or more random variables or observed data values. For example, what is the correlation between height and shoe size of a person? The correlation would be pretty high. They are perfectly correlated if the correlation is 1. So this correlation, I am not sure what the number would be, but it will be higher. Maybe it will be around 0.8 to 0.9. The taller a person is, the greater his shoe size. Demand of a product and its price. This is also correlated. Supply and demand go hand in hand. If the demand of the product is more, its price will be higher. If the demand is less, its price will be lower. What about third? Weight and IQ of a person. Obviously not correlated. IQ has nothing to do with weight. So there can be either very less correlation negative correlation or perfectly random. These weight and IQ appear to be perfectly random. Correlation does not imply causality. What it means is that a greater shoe size is not caused due to a greater height. Right? They are correlated means they move together. Does not mean one causes another. Right? Now let's see. So now what we will do, what SST will try to do, it will model the delay of a single path in terms of mean and standard deviation. So this is the formula. So it will the delay of a single path. The n is the number of stages. So standard deviation increases as n increases. Right. So as the number of stages increases, the standard deviation increases. Rho is the correlation. If rho is 1, the effect adds up as the number of stages increase. Rho is 0, the effect tend to cancel each other as the number of stages increase. Now let's see one example. What it means is that, so look at this path. It is a multi-stage path. 1, 2, there is an n. The combination stage is NCP. If let's say for a particular device, now I am calculating for a particular device. Let's say for device 1, for this one, I know the standard deviation. I will know the standard deviation easily. This data can be calculated by SSTA. Obviously, we need some data from Foundry also. But let's say we know the standard deviation of this. So, in a perfectly random case, where let's say that the delay of this device is independent of delay of this device. In this case, the square root law follows. That means sigma square TCP is equal to sigma square 1, sigma square 2, sigma square 3 till sigma square NCP. Assuming the sigma square of T NAND is same, sigma is same for all the NAND gates, which is possible. For all the NAND gates will show same sigma. Sigma square TCP is nothing but n into sigma NCP into sigma square T NAND. So we rearrange and we find that this particular sigma, so standard deviation is calculated as sigma. So for a particular delay of a single path, n stage path, you will have two values. One is the sigma, other is the mean. Mean is nothing but the addition of mean delay for each of the cell, each cell in this stage, right? So if you have n NAND gates in this example, the mean will be simply n into the average delay of the typical delay of one NAND gate. Sigma, now the calculation of sigma depends on whether they are correlated or not. Now we'll assume for now that delays are perfectly random. They are not correlated. That is, delay of 1 because of the process parameter variation will be independent of delay of 2. So in that case, sigma of the total path will become 1 by square root of the total sigma. So it follows the square root law. Let's see some example. Now please note, we are considering this case. We are considering the case where rho is equal to 0, where the effects tend to cancel each other. Now let's see a path. Let's see 50. Let's say you have 50 gates. Each n21 means 20 is the mean. This is the mu value. This is the mu value, and 1 is the sigma. Now, in a deterministic SCA, in a regular prime time run, you will find that the max delay would be, so the OCV would represent the 3 sigma. So that's why we multiply it by 3. So this 3 is sigma is nothing but value of sigma is 1. So OCV and deterministic STA will try and limit the guard band between minus 3 sigma and plus 3 sigma. So the worst case delay would be mean plus 3 sigma, which is 23. Min delay would be mean minus 3 sigma, which would be 17. If they are perfectly correlated, then this is for every gate. Each gate will have max delay of 23, min delay of 17. if all the gate delays are perfectly correlated, which is what is assumed by OCD method, all of them will show worst case value for max path. That means the total max path delay would be, or 50 gates would be 50 into 23, or it would be, what is the mean value of 50 gates combined? It is 1000. 20 into 50. What is the sigma value? Sigma value simply is the addition. 50 into 150. So, or it will be 1000 plus 3 into 50. Mean plus 3 into sigma. From both cases the value is same. This is what deterministic SPA does, right? It will assume worst case value for every gate, but in real it will not happen. In most of the cases, the delays, some will be fast, some of the gates will be slower, and the effect will tend to cancel each other out over a long path. And that is mathematically modeled by the square root law. Now the sigma will not be 50 for the combined path. The sigma will be square root of 50. Sigma will be square root of 50 according to the random variable law. So it will be 7.07. So what is the max path delay? It will be 1021. This is what we mentioned. We say that the deterministic SPA will overestimate the delay of long path. It's overestimated 1150. Whereas in SSTA we found that if we assume the delays to be random, perfectly random, we get a value of 1021. This is less. This is, I would say, this is more accurate. But obviously there are some conditions. We have assumed that all the variables, all the gate delays are random of each other, right? Okay. So SSTA removes pessimism. Worst case process corner will be determined by this. These are die-to-die variations. These are systematic variations. These are random variations. Worst case product corner potential. So we don't. The SSTA does not target die-to-die, which is, or does not target systematic. It only targets the random effects. That's it. It only targets this effect, random effect, nothing else. So rest all the things remain same. For die-to-die, the corner-based SPA use the corner, an operating condition for die-to-die. Same thing will happen in SSTA. But what about the within die random? So this SSTA will only reduce pessimism from within die random variables. Instead of square of random sigma square of random, it will do 1 by NCT. That means it depends on the particular path. How long is the path? The longer the path, the more pessimism it will remove. The shorter the path, the less pessimism it will remove, because the pessimism builds up as the path stage number of stages increase, right? Okay. So don't worry if you don't understand much of this stuff. When you start working in industry, you will obviously come across it. So ideal SSTA system, the effect of a particular variation on delay is modeled statistically. Correlation is identified. This is the most difficult and most challenging step of SPA. The correlation is identified between variables, and this is where the thinking is changed. Slack is not a deterministic value, but again a probability distribution. It does not say whether your timing is met or failed. It says that your timing is met with this probability. It's a probability distribution. So a statistical timer engine so a static timer, a normal prime time static timer engine needs netlist plus assertions is just constraints, delay and slew models. What it gives you the slack value, right? It gives you the slack value, and it gives you some effect to do diagnostics. What SSTA adds over it, it needs statistics of the sources of variability. It needs some data from Foundry. It needs those mean and sigma values for the process variation, and it also needs the dependence. That means how are the variables correlated. This is the most difficult part. The foundries they have no good way of giving this data. They are not ready to give away this data very easily. A lot of testing would be involved, and apart from giving the slack, it actually gives the yield directly. It tells us that this is your yield. With this particular timing violation, this is your yield, right? So it tells us that. Obviously, the path that is shown to us as violated will probably not violate at a typical corner. Even if we don't solve some timing violation, we will have some amount of yield, although it will be lower. So this will give us the yield number also, some yield number, right? Example. Let's say we see the example of channel length variation. Tool needs information on distribution of channel length. Tool calculates the distribution of gate delay, right? So parameter is this distribution of T, and it will calculate the gate delay. Tool will calculate the gate delay. A lower channel length will have less gate delay. A higher channel length will have more gate delay. The mean will correspond to some typical value, right? So if we give the tool the effect of channel length variation, and we tell the tool that what is the formula to calculate delay, it will calculate the delay from the channel length variation distribution. This is what the ideal SSTA system will do. So a delay report for SSTA will look something like this. For every gate, it will have a mean and a sigma value, and combined it will give you a path delay. This is the path delay. So it will give again a mean and a sigma value, and it will give some kind of a graph like this, where the slack curve is again a normal distribution, and you say that okay, at -3 sigma the slack is -0.12. So if you want to sign off till -3 sigma, you will have to move this curve on the right side. You will have to make the fixes, right? You will have to make sure that -3 sigma value is 0. Only then you can say that I have signed off my script for -3 sigma, right? So this is where SSTA differs. It gives the yield numbers in terms of sigma value. So here what is the yield? The yield is somewhere between -2 sigma and -3 sigma, somewhere between 95% and 99%. So it gives, for every path, it tells us what is the sigma, what is the mean. If mean -3 sigma or mean +3 sigma, depending on whether it's a setup path or a hold path, if it violates, so you can report timing up to 0 sigma, up to 1 sigma. So report timing 0 sigma means you get only the mean value. You can report timing +3 sigma for setup case. You can report timing -3 sigma for hold case, for example. So this is how things are done in SST, statistical work. So it is with the increased number of, what is the need? With the increased number of corners, pessimism is increasing. If there is a lot of pessimism, then you are unnecessarily wasting your time and energy in solving paths with greater pessimism. SSTA will reduce the pessimism for random process variation, and it will help you in closing the timing much easier. The process becomes much easier. Obviously, there is a shift in thinking. Earlier we thought in terms of slack being 0. Now we think in terms of slack being met till 3 sigma or -3 sigma, and so on. So this is the difference. These are the references I use to make this presentation. You can go through this if you want, if you are much more interested in this topic. I will just now speak about a couple of things which are not there in the slides. So what is the situation now? In present day, SSTA is not being used 100%. In last session we saw that there is an advanced version of OCD called AOCD, and there is also one thing called POCD. So AOCD and POCD both, they try to bring some advantages of SSTA into a regular STA tool. How do they do that? For example, in AOCD there are two things. Now it replaces OCD and it replaces by two things. One is the number of stages. So in case of AOCD, the delay of a particular path will depend on the number of stages in a particular path, and it will also depend on how far are the cells away from each other. So prime time needs two tables. One is the stage table. So what happens in stage table? Stage table, what happens? It mimics the SSTA standard deviation calculation, that table. What it does, as the number of stages increase, the derate will decrease. So let's say if you have 2, number of stages 2, the derate will be, let's say, 1.1. If the number of stages are 10, the derate will be 1.08. It is mimicking the standard deviation square root formula of SST. What it is telling us that if the number of stages increase, the random effects will kind of cancel each other out, right? So the derate will be lower. You have to remove more pessimism as the number of stages increase. This is the way how random variables are modeled in AOCD. The second factor here is it needs a location based table. That means it needs that, okay, if the two cells are far apart, so the table describes that okay, if you are this much far apart, then this derate will increase or decrease. So now it is modeling the correlated correlation of the variation. It is saying that as if the cells are closer together, the derate will be less. If the cells are farther apart, the derate will be more. So the cells that are close to each other have less derate and therefore less delay. The cells that are farther from each other, they will see some of the effects which are specially correlated, so the delay is more. So there are two factors. One is the location based derate. This is called location based. So AOC is combined of two things: location based derating and path based derating. Both location based derating tries to model the specially correlated variables, and path based deration tries to model the random variables. So this is how we are taking. So right now, since we are not 100% into SSTA, we are taking the good things of SSTA, which can be modeled easily inside a regular STA tool, and the tools the EDA companies are trying to reduce pessimism. So once you are comfortable with this course, once you are comfortable with STA, you can actually try your hand at AOCD or even POCD. POCD is slightly different variation over AOCD. So you can read more about it. These are the resources about statistical STA, and unfortunately I don't have any lab which shows this. The lab is not easier to model because you need a lot of data. You need some tables which I don't have access to. So you can read about it. This is a very nice article, the good, bad, and the statistical, the first one. You can read more about it, and but for all your practical purposes, you will be using OCD for some time, and then when you go into industry, you will see that you will start using more and more of AOCD and POCD. Thank you.